Right, so vectors are important because they make us do things when we're talking about physics, and it really kind of pulls everything together and makes things work a little bit more nicely. All right. So before we can talk strictly about what vectors are, we have to define these two things. Right. The first is a scalar. Right? I've heard people call it a scalar. Like, ooh, the scalar. No, it's not a scalar. My first year teaching, we were talking about Copernicus and what he did to talk about like motion way back when, and a kid called him Copernicus. I'm like, no, it's Copernicus. All right, so a scalar is any quantity, right, that has a magnitude only. Okay, so that's important. That a scalar is anything that has magnitude only. Okay, so what do I mean by magnitude? Madhu, thanks for raising your hand. What do you mean by magnitude? Yeah, quantity, the amount, right? So magnitude just means amount. Okay, so we're talking about, like 75 kilograms. The magnitude would be 75. If we're talking speed and we want to say 37 meters per second, the magnitude is at 37 meters per second. Okay, it's the amount that you have. All right, some scalars would be time, right? Mass, speed. And there are others, right? Energy is a scalar. Okay, there are all kinds of other scalars. But scalars, think of them as just regular old numbers. Okay, they're just random numbers, not random numbers, but they're just numbers, and we can deal with them any way we've always dealt with them. Add them, subtract them, multiply, divide, all those things. Okay. The other is your vector. Your vector is a little different, where it has magnitude, but it also has direction. And that's important, right? The direction part is what's important. Okay? Because the direction tells us how we're going to deal with these quantities. And when I say quantities, again, I'm talking things that we've talked about in class, like speed, acceleration, displacement, direction, all that. Okay? Time. Right? So, but that direction is very, very important because it plays a major role in how these quantities are going to interact. So far, when we've talked about vectors, things that we've talked about so far, velocity is a vector. Okay? Acceleration is a vector. Right? Think about that chart that we talked about, that you filled out on that quiz, right? It mattered what direction they were pointing in, right? The direction told us whether it was going to speed up or slow down. Okay? So that's one instance where direction is very, very important, is just by, hey, if they're pointing in opposite directions, velocity and acceleration, the object's going to slow down. Okay? If we had just said, all right, your velocity is 7 meters per second and your acceleration is 2 meters per second squared, that doesn't tell you what's happening to the object, right? It doesn't, because we don't know which direction those things are pointing in, so it could be speeding up or slowing down. So that's where direction is important. Direction becomes even more important when we start talking about forces. Okay? So next unit we'll start talking about forces, and that's when it gets really important, and the direction that objects are being pushed really matters. Okay? So scalars, again, they act like any regular old number. Add them, subtract them, good to go. Vectors, not so much. They're different. Okay? That direction, again, is very important. So you can't just add them, subtract them, things like that. You have to pay attention to what direction they're going in order to perform functions on them. Okay? All right. So scalars kind of is what it is. We're going to leave them alone. Right? You guys can do scalars. It's pretty simple. Vectors are a little more important, a little more involved. And they're going to make our life a lot simpler when we get to projectile motion, is when we put X and Y motion together. Okay? So you guys looked at, seems like forever ago, but you did that vector walk activity, right? The vector walk, right? And you had a guy walk like this way, and this way, and that way, and this way, right? And you found that the result would be this, correct? Okay? And what happened when you jumbled them all up? You jumbled up the directions. What happened to the result? It was the same, right? And you jumbled it up again. And what happened? It was the same, right? And you could have done it a million more times. Any combination you would have come up with of all the same vectors. Essentially, they're vectors, they're displacement vectors, because you're walking a certain distance in a certain direction, right? And the result would have come out the same. Okay? So clearly, we can see right away. You guys learned two things, and you didn't even know it. One, you figured out, or you learned the method for how to graphically add vectors. Right? So graphically meaning drawing. When you're going to add them graphically, you draw them what's called tip to tail. Okay? So you take if you draw your first vector, and when you want to add your second vector, you just take the tail of the second one and connect it to the tip of the first one. And you just keep on going like that in a line. Making sure that you keep the length of the arrow the same and the direction it's pointing the same. Those are the two important things. Okay? Because the length of the arrow is the magnitude of it. It's a scale. It gives you an idea of how large the vector may be. Right? So if one vector is velocity and it's 10 meters per second, and the next one is 15, obviously the 15 should be longer than the 10. Okay? So that scale is really important. So it's nice drawing this on the computer because the computer will give you those scales perfectly good to go, right? When I learned it, here's a ruler, here's a protractor, and draw them out, setting your own scale and drawing them at the right angles and all that. And you know what? Everybody got a different answer. They're all kind of close, but off. Why do you think? Why do you think they're all a little bit off? Yeah, everyone draws them a little differently, right? So the graphical method is great for understanding how to add vectors, but it's not necessarily the best way, right? We can do it using math and it becomes a whole lot easier, okay? The second thing you learned, again, aside from the tip to tail, is that you can draw vectors in any combination you want. And as long as you keep the length and the direction the same, you'll get the same resultant. So it's kind of like walking in a maze 50 times and making the same moves, but making them in different orders and getting to the same place. Okay? So that's essentially what it does for you. So if one way doesn't work, just jumble them up a little bit. It'll get you there anyways. Okay? So, what we've dealt with so far has been motion this way, right, in the x, and motion this way in the y. Correct? And we can do those, right? The kinematic equations will help us. But this isn't really real life. Right? If everything was perfectly horizontal, we'll just call it, no, we won't call it that. We'll call it, if everything was nice and horizontal and vertical, one, life would be boring, but life would also be easy. And we know that neither of those are true, right? We know that pretty much everything, or most things, they travel at some sort of angle, right? Or combinations of angles. So we need a way to make this happen, or to deal with these angles in the framework of horizontal and vertical. Does that make sense? Okay? So again, we need to take what we know about horizontal and vertical and somehow apply it to vectors that are at an angle. Okay? You guys remember SOHCAHTOA? Oh yeah. Here's where SOHCAHTOA comes in. All right. SOHCAHTOA. There are always so many rumbles when SOHCAHTOA comes up and trig comes up. Like, it's not that big a deal. Come on now. I know back from when I did it and when, seeing other kids work, all the stuff you do and you did in trig class. All you need to know from me is this. All right? All you need to be able to do in this class is this. If you can do SOHCAHTOA, even you, Josh, can be successful. Okay? So, this is all we need to remember. So let's look at this. Let's start with a completely new one. So real quick too, you notice how I put this little like half arrow on top of this guy right here? This little half arrow is a vector symbol. This denotes now that we're talking about a vector. Okay? In your book, all right, or anytime you read, there's two different ways you could see it. They may denote vectors. You'll either denote it with the vector symbol or they'll make it a bold. Right? So if we're talking speed, it might be a normal type print V. And if we're talking velocity, it'll be a bold V. Okay? Talking like a force as a vector, it'll be a bold F as opposed to a regular F. Okay? All right, so let's start afresh, anew, and let's look at our friend here, vector A. Okay? Imagine that this is let's say we shot a ball at this angle, right? Like that. Okay? Kind of like a trebuchet, just firing straight out like that. And this is all well and dandy. This is what happens. It's real life. The problem is we don't know how to deal with this. Correct? We can't do that. But we can make it horizontal and vertical, right? And if we do horizontal and vertical, it works out perfectly. Okay? So what we need to do is we need to find a way is can we break this down into pieces that are horizontal and vertical? Can we make this angled thing perpendicular, essentially? Okay? And we can. We know that it's traveling in some direction, some angle theta. Okay? So what I want to do then is I want to take this and I want to break it up. All right? I want to make it into the pieces that build it. So here's what I want you to do. Imagine that we have a light, right? And it's shining down on our vector A. Okay? It's shining down on it. And when it shines down on it, it creates a shadow down here along the x-axis. Okay? When it creates that shadow, we get something that looks like that, right? It's only as long as when it goes from its tail and it shines down on its tip too. It's only as long as that piece, that projection. Okay? We can call it A sub x, right? It's the x part of vector A. Okay? If we then take that light and we shine it over here along the y-axis, we get a similar outcome, but in a perpendicular direction. We can call this A sub y. Does that make sense? The important thing here is that they are perpendicular. So what have we created? A triangle, right? We've created a right triangle. We know triangles, right? You can do triangles. I hated geometry, but I can do triangles, right? Awesome. Are we good so far? Right? So these two little bits we've got here, we call them components. All right? Think of components as like the Lego pieces that when we put the two components together, the two Lego pieces together, we make the vector. Okay? But if it's at an angle like this, we need an x and a y component in order to make this angled piece. Okay? So these two together, when we add them, make this guy. Okay? Well, it's all fine and dandy to know that if we add a sub x and a sub y, we get a. But I can't just type in like a sub y into my calculator and be like, oh, sweet, we're good to go. It doesn't work that way, right? We need some actual numbers. We need a way to figure that out, okay? Imagine that we know how fast this is traveling and we know the direction. So I want to be able to take this and put it in terms of these two pieces. Okay? Does that make sense? Right? So what I want to do again is I want to take it and I want to put it in terms of things that I know. All right. So if I look at this, I'm dealing with A, theta, and A sub x. Just looking at that and thinking about SOHCAHTOA, what trig function do you think is going to help us? What do you think? Austin? Cosine, right? It's going to be cosine. So let's just do it this way, right? So it's cosine equals adjacent over hypotenuse. So the adjacent would be A sub x. Actually, before we even do this, let's just write it this way first. Okay? So the adjacent is A sub x over A. Okay? Again, now we want A sub x, right? So when I want to find the x component of any vector, it's going to be the magnitude of the vector times the cosine of the angle it's traveling at. Okay? And that's important. That's something that's... Now what we've done is we've taken this angle piece, right, this angle that it's actually traveling at, and we've broken it into something we are able to actually do. Right? Something that we're very capable of doing. Okay, and you guys have proven that. So you remember that equation we dealt with that's like x equals x sub o plus v sub o xt? That v sub o x would be the x component of the speed. So v sub o x, you would type in a cosine theta, right, or 15 cosine of 35, something like that, and get that number. Okay, and that would go in. That's why you have that v sub o x and that v sub o y. Okay. It's very important that you keep them separated. All right. I don't know if I told you, it might have been the other class, but x and y, when you're dealing with equations, you solve problems, they have to stay separated at all times. Okay? They're like gasoline and fire. You put an x and a y, and everything blows up. Okay? You switch them. Okay? Can't do it. So how about now a sub y? How do I find a sub y? What do you think? Looking again, we know A, we know theta. How do I find A sub y? What trig is going to help us get there? Sine, right. So sine of theta is opposite, right? Over hypotenuse, OPP. You guys don't know that song. OPP, Naughty by Nature. You down with OPP? Yeah, you know me. All right, so the opposite side is A sub y, and the hypotenuse is still A. So on this side, we get that. Okay? What do you think? Not too bad? Okay. So we've just taken a vector and we've broken it into components. Okay? Pretty simple, right? And this works for everything. There's only one instance where this is going to change, and you'll know that one instance is very simple. And it's going to be very obvious when it has to change. Okay? But so anytime you have a vector traveling at an angle, you're going to have to break into components. And this is the guy that you're going to use. X gets cosine, Y gets sine. Okay? Make sense? Awesome.